quantum leap. In the early 19th century, it was theorized that at the subatomic level, energy can only be released and absorbed in discrete indivisible units called quanta. This means electrons have fixed orbits around the nucleus of the atom as their energy hums in discrete amounts. When the electron gets excited or de-excited, they will absorb or emit a specific quanta of energy, which will mean they leap from one orbit to another without inhabiting the space in between. This is called the quantum leap. In essence, there are places within the atom that the electron will be likely to be, and other places where they won't, as energy is being absorbed and released in discrete units. Particles behave like waves. There's a famous experiment in quantum physics called the double-slit experiment, which exposed something about particles that still surprises us today. Particles display both particle-like and wave-like behavior. In a version of the experiment, on a larger scale, we have a gun that shoots tennis balls one by one at a detector, which will register where the tennis balls land. In between the gun and detector, we place a barrier with 2 slits, which will leave openings for any tennis balls to go through. Over a period of time, and after many tennis balls, a pattern emerges on the detector, indicating where the tennis balls have landed. The results show that the balls which have not been blocked have landed directly behind the slits in the barrier. If we replicate this experiment but on the subatomic scale and use electrons instead of tennis balls, we expect similar results. But this was not the case. Scientists found that when the gun shoots electrons one by one toward the detector and past the double-slit barrier, the pattern that emerged on the detector looked like this. The electrons landed not just behind the 2 slits, but in narrow strips across the length of the detector, and a significant number of electrons even landed straight behind the middle of the barrier. The pattern that emerged is an interference pattern and is associated with the behavior of waves. Imagine we have 2 waves that interact. The peak of the waves will combine to form a higher peak, and the troughs will combine to create a deeper trough, and when a peak and trough meet, they will cancel each other out. So if we imagine that our electrons are less tennis ball-like and more wave-like, then what happens? This is a wave from above. The black lines represent a peak, and the spaces in between are the troughs. When an electron goes through the double slit, its wave is split in 2, and these waves then interact. The peaks meet here and reinforce each other, creating higher peaks, and the troughs meet here, also reinforcing each other, creating deeper troughs. And here a peak and a trough meet, cancelling each other out. The interaction between the waves results in the interference pattern at the detector screen. Where the waves are most intense, we find more of the electrons on the detector screen, and where they cancel each other out, there are no electrons on the detector screen. Erwin Schrödinger came up with an equation for the electron's wave function, and using this equation, we can find out the probability of the electron being in a particular location. Think of the wave as a bundle of probabilities, and the size of the wave in any location predicts the likelihood that the electron will be found there if it is looked for. That is why on the detector screen we observe most of the electrons landing in the places where the electron's wave is at its most intense. It seems as if the electron is not in a fixed position but has different probabilities of being in many different places at once. The act of measurement. To observe the electron's wave function going through both slits at the same time, detectors were placed next to the slits to capture this activity. But when this was done, something strange happened. The electrons stopped behaving like waves and went through one or other of the slits and landed on the detector screen to form the 2-striped pattern rather than the interference pattern. It seemed as if the act of measuring did something to collapse the wave function. The superposition principle. The superposition principle states that while we do not measure the electron for its position, it is in all the possible positions it could be in at the same time, and when we observe it, the superposition collapses. So in this illustration, when our detector is off, our electron is in all of the possible positions or states it could be in simultaneously. But when we switch our detector on, the superposition collapses and the electron gives up all of its possible states to choose just the one. That is why we were not able to observe the electron's wave function going through the double slits. The very act of attempting to observe made the electron's wave function collapse. The electron gave up its superposition and chose just the one state to be in, i.e. the electrons actually reverted to particle-like behavior, and that is why instead of going through both of the slits, the electrons that landed on the back detector chose to go through either one or the other of the slits.